Looking at the question from the November 2015 Department of Education paper on vertical projectile motion, and this was quite a tricky question. And it starts off saying ball A is projected vertically upwards at a velocity of 16 meters per second from the ground. Ignore air resistance and use the ground as zero reference, which is going to be important for any position or displacement time graph we draw, not for velocity time graphs though, because you can't see the reference point on them. The first question says calculate the time taken for A to return to the ground. Okay, they've given you a sketch here, and if ever you're not given a sketch, it's always a good idea to draw a sketch and add as much information onto that sketch as possible. I always say to my students, and I hear lots of teachers say, if you walk out of that exam and your question paper is completely clean, then we're worried. The more you write, the more you draw on there, the more you write notes for yourself and things, the better it is for you at the end of the day. So we're going to calculate the time it takes for A to return to the ground. Okay, we're going to plug in. Okay, we've got our final velocity. Okay, and how you choose to do this. Okay, what I also quite like with vertical projectile motion is drawing a little sketch next to what you're doing and highlighting the section that you're using. So I'm going to use the section from here to here, okay, which is obviously not the entire time the object is in the air for, but then I'm just going to double it to get the total time. Because the motion is symmetrical, if it takes a second, let's say, to get to the top, it'll take a second to get to the bottom, and so that's what they mean by the motion is symmetrical. So I'm going to do this as 0. The initial is 16. Okay, something that we should do or decide beforehand is what are we choosing our signs as? I'm going to choose upwards as positive and downwards as negative when it comes to this motion. Now they can sometimes force you to make down positive, so it's a good idea to practice that every now and again and just change it up a bit in case it happens. Okay, and then G is going to be negative 9,8. Okay, so let's pause for a second and just take a look at when are things going to be positive and when are they going to be negative. If you make up positive and down negative, okay, when it comes to velocity, that one's nice and straightforward. Okay, if the object is moving upwards, then it's just a simple positive velocity, and if the object is moving downwards, then your velocity is negative. Okay, so very easy to figure out. Okay, acceleration is a little bit trickier. Acceleration doesn't just have to do with the direction that you're moving in, it also has to do with are you accelerating or decelerating. Okay, so if you are, let's look at A's motion. Okay, for the first part of the motion, that object is moving in the original direction. Okay, so original direction, okay, which we've assigned as positive. Okay, and then you're looking at whether it's accelerating or decelerating on its way up. Now, this ball is going to go slower and slower and slower and slower, and eventually at the top, the final velocity will be 0. So this object is decelerating. And decelerating, if you think back to grade 10, if an object was decelerating, you would substitute the acceleration in as a negative. In this case, we're just going to sub in the gravitational acceleration as a negative. Okay, so acceleration has got to do with two things: the direction you're moving in and whether you are accelerating or decelerating. So if an object is moving in the original direction, if you've made that the positive direction, that is, okay, which is I think is a little bit easier, and it is decelerating, which is a negative acceleration, a plus times a minus gives me a minus. If you look at the other side, the object is heading in the opposite direction. Okay, and the opposite direction we've assigned as the negative direction. But in this case, when the object is heading downwards, it's actually going faster and faster and faster and faster. Remember what happens during vertical motion. Okay, if we hypothetically, let's just choose a nice value here. If we say that the object starts with a velocity of, let's say, 19.6 meters per second, then what's happening is every single second, this object's velocity on the way up decreases by 9.8 meters per second every second. Okay, so after a second, its speed will be 9.8, and after another second, its speed will be 0. And then on its way down, it will do the opposite. It will speed up by that much. So after a second, its speed will be 9.8 meters per second. And then after another second, it will be 9.8 meters per second faster, which gives you 19.6. Okay, so that's what's happening during the motion. So on the way down, the object is moving in the opposite direction, which is the negative direction, but this time it's speeding up and the motion is symmetrical, which means if the original velocity of this ball was 16, then on the way down it should be negative 16. It should be symmetrical. If it carries on going below the original starting point, obviously the velocity will just keep increasing, but if it lands on the same point it was released, your motion should be symmetrical. So if it's opposite direction, which is negative, but it's accelerating, which is positive, but a negative times a positive once again gives me a negative. Okay, so it's quite a lot to think about. Then when it comes to displacement, okay, your displacement is positive if you end above your starting point, and your displacement is negative if you end below your starting point. Okay, that is of course if we're choosing up as positive and down as negative, which we'll do most of the time. So let's look at some examples of this to illustrate that. So let's say, for example, you're throwing a ball up and then it lands here. Okay, and I should probably add it ends above your chosen starting point. Okay, what I mean by that is if, let's say, we work out the displacement for this highlighted section, then that is my starting point, my VI, and this is my end point, and I have ended up above my starting point. So my displacement will be or in this case delta y, will be a positive value. If I choose another section, let's highlight that in pink, and we say, let's say you're starting at the top there. In other words, your VI is 0 there, and you end here. Then you are ending below your starting point, and then your delta y, or displacement, will be a negative. Let's say that you look at the entire motion, so from start to finish. Okay, and this is my VI that I'm choosing to sub in, and this will be my V final. I am ending below my initial starting point, my chosen starting point. So my displacement here will also be a negative value. Remember that delta y stands for displacement and not distance. So when you sub in or calculate delta y, you will be subbing in the shortest distance from your start point to your end point. Okay, so even though we draw the motion like this and it looks like it moves like that, it's actually moving up and down, okay, on the same plane. So we actually start here and we end here. So our shortest distance from start to end point is this distance here. Okay, so if this entire height was, let's say, 8 meters, but this was 5 meters, my displacement is actually just 5 meters. It's my shortest distance from my start point to my ending point. Okay, so that's what you look at to decide whether displacement is positive or negative. Okay, getting back to this. So we said we're choosing the highlighted section. We'll end up taking that over. It becomes negative 16. We divide by negative 9.8, and you get a time of 1,63 seconds. Okay, which then is only the time to get to the top, so we need to times it by 2. So it's right here, total time, okay, is 1,63 times by 2, which gives us 3,27 seconds. So this value is actually 1,6327, and I'll generally keep values as 4 decimal places until I get to the very final answer. So it's actually that value that we've times by 2, okay, and then at the end we can round off to 2 decimal places and say it is 3,27 seconds for the entire motion. Alternatively, if you want, you could have subbed in the initial velocity as 16, and your final velocity is negative 16. Okay, that way you don't have to times by 2 at the end of the day. You're basically saying, and again, let's draw and highlight the section that we're using here. Very useful. Okay, we are using from there to there, so we're using the entire motion. That's why we're subbing in the positive 16 and the negative 16, and then you'll get a time also of 3.27 seconds, and you're not needing to times it by 2 because you are looking at the entire motion from the get-go. Then the next question asks us to sketch a velocity time graph for ball A, and we have to show the following. Now, even if they don't tell me to show anything, I will show as much as I possibly can on the graph if I've calculated it or if I have it. So they want me to show the initial velocity of ball A, the time to get to the highest point, and the time taken to return to the ground. So velocity time graph starting at the velocity of A was 16. Let's extend this into the negative. Okay, so the velocity starts as 16. Then, let's take a look at the motion again. On the way up, my velocity is decreasing, decreasing, decreasing until I get to the top and my velocity is 0. Okay, and it's doing that at a constant rate. In other words, the velocity is decreasing by the same amount every single second. And that amount is 9.8 meters per second every second. Okay, so your gradient here needs to be a straight line. Why? Because the change in v over change in t, or gradient, in other words, gives me my acceleration in a velocity time graph, which in this case equals to the value of g, negative 9.8. And that's a constant, that doesn't change. So in this section, your velocity time graphs will always be straight lines. They will never curve. If you find yourself drawing a curved velocity time graph, you know you've done something wrong somewhere. Then on the way down, my velocity is increasing, increasing, increasing until I get to negative 16. Okay, again, still at a constant rate. Okay, so it's super important that your graph looks like the line's gradient is the same. If you end up making your graph look like that, you'll lose marks because your gradient doesn't look the same throughout. Okay, we know that the final velocity was negative 16. We know it took us 3.27 seconds for the entire motion and 1.63 if we're doing that to 2 decimal places for the ball to get to the top height. Okay, remember what this means. When your graph touches the time axis, that means your velocity is 0 because your velocity is 0 at that point. And the minute your graph goes below the line, that means that your object has changed direction. Now the question doesn't ask you to draw a displacement time graph, but let's compare it to a displacement time graph for a second, because it's very easy to confuse your graphs with each other. So on a displacement time graph, we are showing the motion of the object, but the ground is the 0 reference. In other words, that line there is the ground. In other words, the person who's drawing the graph is standing on the ground and looking at this whole motion. So the ball starts on the ground. Now, the gradient of a displacement time graph gives me my velocity. So whenever I teach this, I will end up asking, what is happening to your velocity on the way up? And what is happening to your velocity on the way down? And my learners always say, why are we asking this when we're drawing a displacement time graph? It's because you want to be able to figure out what's going to happen to the gradient of your graph. Because your velocity is decreasing while it's moving up, your gradient should also be decreasing. So your gradient is decreasing on the way up. And because your velocity is increasing on the way down, your gradient should be increasing. Now be careful, this is a displacement time graph. In other words, it's showing the position of the object as well. And your object started on the ground and it ends on the ground. So it needs to end back on the ground again. So you need to go back towards the ground, but this time your gradient should get steeper and steeper and steeper. And you've got 3 options. Okay, option 1, 2, or 3 here. Think to yourself, in which case, let's change the shape a little bit, in which case is the gradient of the graph getting steeper and steeper and steeper? If this was a hill you had to like cycle down, where is it the scariest hill? 1, 2, or 3? 2 is getting flatter and flatter and flatter at the bottom. 3 is getting steeper and steeper and steeper. So 3 is the scary one because it's getting steeper and steeper and steeper. So we make our graph steeper and steeper and steeper, trying to make your graph look as symmetrical as possible. Might be easier just to draw the whole thing from scratch like that. Okay, and then you can insert your values if you've worked out the max height and so on. Okay, so very, very different graphs. They're showing very different things. In both cases, you ask yourself what's happening to the velocity because it helps you with the gradient of this graph, but it shows you very different things. Then the last question, which quite a tricky question. So ball A was thrown up, it goes up into the air, it comes back down again. Now, 1 second after ball A is projected upwards, ball B is thrown, not dropped. Dropped means my initial velocity would be 0. So ball B is thrown vertically downwards at a velocity of 9 meters per second from a balcony which is 30 meters above the ground, when they've given that on the sketch. Okay, so we need to make a note here somewhere that ball B is thrown 1 second after ball A. Okay, so let's start from scratch. Okay, so they've given us two objects. Immediately I feel like it's probably going to be a simultaneous, but let's see, sometimes it feels that way and then you end up having enough information to solve one of them. Okay, we're going to make a note here that the ball B is thrown a second after ball A is thrown. And you want to know, calculate how high above the ground ball A will be at the instant the two balls pass each other. Now when they pass each other, okay, no one is saying where they pass. A lot of people mistakenly think they'll pass each other halfway or when A is back on the ground, and we just don't know something like that. Okay, so ball B is in the air when they pass each other. Think about whether it's in the air for a second longer than ball A was or shorter than ball A was. So ball B, because it's thrown 1 second later, it spends 1 second less time in the air. So its time in the air is actually time that A spent minus a second. So it's a second less that it's in the air for than A. So let's write down everything we have. Okay, ball A's initial velocity was given to you as 16 meters per second. Let's just remind ourselves again, because this is where I find my students were most likely to make a mistake in this question. Okay, it's to do with the minus signs. Then you know that the value of G is negative 9.8. Ball B's initial velocity was 9 meters per second, but okay, it was thrown downwards. And we chose down as negative. And velocity is straightforward. If you're moving up, it's positive. If you're moving down, it's negative. Let's just emphasize that and put a plus in front of A's velocity. Okay, then this one we're going to make just a T. Okay, because it's in the time in the air is just T, and B was in the air for 1 second less than A. Okay, now that's what we know at this point. We don't know how far A or B travels when they meet each other, but they did give us the total distance, and surely that must be important. So we're going to make this distance, okay, sorry, delta y, because it's vertical. Okay, we're going to make the distance that A travels a distance x. Okay, just because the x looks so familiar, you're so used to it in math, so it might make it look a little bit nicer. And then we're going to make the distance that B travels. It can't also be x. If it's also x, then you're saying they meet at the exact same, they've traveled the exact same distance when they meet. Okay, we know that the total distance once they meet, let's say they meet here, okay, that total distance needs to be those two added together, right? A might travel, let's draw this on a sketch. A might travel 8 meters, let's say hypothetically. Okay, so when A is moved 8 meters, B would have then moved 22 meters. So we know the two distances have to add up and give me 30 at the end of the day. It doesn't matter what happens or where they meet each other. Now, this again is a place where mistakes tend to happen. So A travels upwards, so we'll make it a positive x distance. Now be careful, I'll do this in a different color. B ends up traveling down at a certain distance. So we're going to make it, first of all, 30 minus x, okay, because these two have to add up and give me 30 at the end of the day, which it will. But not just that, you need to put a minus in front of this whole thing, okay? Because B ends up moving downwards. So in other words, if you think about what we said earlier, it ends up below the starting point, and that's why it's a negative displacement. So we don't know what the speed of either of these objects are when they meet. So we don't have V final for either one of these. And the only equation that doesn't have V final in it is this equation. Okay, so we're going to sub this into this equation. We're going to sub in everything we have. Okay, so A's distance, we're going to make an X. We know its initial velocity was 16. I'm just going to make this a T, make it look a little bit simpler. G is negative 9,8, and this once again is T. Okay, then B, you are obviously welcome to say that B spent a time T in the air, and then A would have spent a time T plus 1. In other words, 1 second more than B. So whether you say A spent 1 second more in the air than B, or you say B spent 1 second less than A, boils down to the same thing. Okay, so it's your choice. Then, now careful here, you're going to say negative brackets 30 minus X, okay, because it's ending below the starting point. And then we're going to sub in the values. Again, be careful of the negative because it's on its way down for ball B. T minus 1 because it spends 1 second less in the air than A. G is negative 9.8. And then T squared. Okay, and at this point it really just becomes a math problem. You've sorted out the key things in science. Okay, so let's try and simplify this as much as possible. Okay, we're going to just say X is equal to 16T. Okay, plus times and minus gives me negative 4,9 T squared. This is my first equation. Okay, then we're going to times this in and get negative 30. So easy to just make a little math error here and then get demoralized in this question. Okay, minus 4,9 T squared. Okay, double check that you haven't made any errors here, and I have. Okay, we forgot to make this T minus 1 squared, and then we need to multiply this by T minus 1 squared. Okay, equation 1 is very simple, but equation 2 we need to work on and try and simplify this as much as possible. So we're going to go negative 30. In fact, let's take that over to the other side. No, negative 9t plus 9 minus 4,9. Let's times this bracket out. Okay, don't make the mistake of forgetting the middle term. If you're scared you're going to do that, write your bracket twice. Okay, and do your distributive law. Okay, which then becomes, let's keep the 30 here for now. Okay, don't rush this. Like I said, it's so easy to make a mistake here and then to mess up your calculation. Okay, this will become negative 2t, which a negative times a negative will give me positive, and 2 times 4,9 is going to give me 9,8 t, and then minus 4,9 here, and then I'm going to take that 30 over, okay, because I'd like x by itself, and just be careful it becomes a positive 30. Okay, again, let's try and simplify this as much as possible. Okay, so let's say we've got our two equations now. Okay, we're going to equate these two, so we're going to say 16t minus 4,9 t squared is equal to negative 9t plus 9 plus 30. Okay, and now it's just a case of solving for t, which feels like it's going to be a big issue and you're going to end up with a trinomial, but immediately negative 4,9 t squared and negative 4,9 t squared, if you were to take that over, it would become a positive. That's going to cancel out. Okay, now it's just a case of getting all your t's to one side and all your numbers to one side. Okay, so we've taken all the t's to the left, and now we end up with 15.2t is equal to 34.1. Then we divide by 15.2 on both sides, and we end up getting a time here of 2,24. Again, I'm not done, so I'm going to leave this as 4 decimals as a rule. And the question at the end of the day was to calculate how high above the ground ball A will be at the instant the two balls pass each other. So we haven't answered the question completely yet. We now need to figure out the height of ball A. So let's go sub into ball A. We're going to go okay, we have the initial velocity, we now have the time, 2,24. I'm going to keep this as 2,2434 in my calculator. And then we should get a distance of 11,323 meters height is where these two meet. Okay, so A has traveled 11,23 meters when it finally meets ball.